Welcome, everybody. It's my pleasure today to introduce Ximena Fernández, and she'll be telling us about Morse theory for group presentations and the persistent fundamental group.
Okay, thank you very much for the introduction. Also, thank you very much for the invitation. I'm really happy to be here in this nice seminar. Okay, so today I'm going to talk about discrete Morse theory and two different applications related to the use of discrete Morse theory in different problems related to group presentations. In particular, I'm going to show two applications. The first one is related to an open conjecture in combinatorial group theory that is called the Andrews-Curtis conjecture. And the second application is related to some sort of description using group presentations of the persistent fundamental group of point clouds. Before doing that, I'm going to show you a refinement of the classic ideas related to discrete Morse theory. And of course, we are open to apply these ideas in your own problems if you can or you want to. So let's start. Let's see, I'm not able to. Yeah, so now let's start with the motivation. So motivation comes from a combinatorial homotopy theory. And the idea will be to try to understand topological spaces using some combinatorial structure that as a model of this topological space, and also to try to find some ways to simplify this combinatorial structure in order to understand better the homotopy type. And a very, let's say, foundational way to simplify the structure of a complex is the notion of collapse. So every time if you have a complex, CW-complex, and you identify a pair of cells satisfying some conditions in terms of the attaching maps, sometimes called that you have a pair of cells and one cell is a free face of the other, then you can perform the collapse. And then you simplify the structure of the complex and you don't change the homotopy type. And in particular, you can iterate this procedure. So you have a complex and you can identify some ordered set of pairs of cells, and you can perform these collapse, also these elementary collapses, and you obtain some simplified version of your original complex. And sometimes, like in this case, you can start with a ball and then you obtain in the end a point. So you're proving in this case that the complex is contractible. But in general, this is not the case that you are so lucky and you can really simplify so much your complex. It might be the case that you don't have any pair of free faces at the beginning, or you have some set of free faces and then you get stuck at some point. So we're going to see that discrete Morse theory is, in a way, some sort of generalization of the notion of collapsibility developed by Whitehead in the 30s. So you probably know the main idea of discrete Morse theory, that it's again to simplify the cellular decomposition of a complex without changing the homotopy type. In this setting of discrete Morse theory, you work with regular complexes, like in this example. So the touching maps are homeomorphisms. This will be our one example in the talk. And you define a Morse function, so some labeling of the set of cells that satisfy this condition in gray. And then according to this Morse function, you can classify your cells between critical cells and non-critical cells. So here critical cells are in orange, and these two kind of cells plays a different role. So every time you have in the levels of complex, if you have a critical cells, then you change the homotopy type, but every time you have non-critical cells, non-critical cells come in pairs that are associated to collapses. Okay, so every time you have a pair of critical cells, you can remove them from the levels of complexes and you don't change the homotopy type. So you have two different kind of situations. And well, so the main theorem in discrete Morse field tells you that if you have this set of ingredients, so you have a complex, a Morse function, and a set of critical cells, that you have a complex. In this talk, I will denote it by Km. This is a simplified version of your original complex. And this complex has one cell of dimension K for every critical cell of index K. So in this example, this is the set of critical cells. So this theory and some other corollaries or versions of the theory allows us to perhaps understand better the structure of K, and in particular, it's very useful when you try to understand the homology of K more efficiently in terms of the cellular decomposition. But in this talk, we're going to be interested in the homotopy type of K. And in this, at least in this statement, we don't have the description of the attaching maps of K, of this reduced complex. So, I mean, in this example, for instance, we really don't know which is the homotopy type of K. Only with the description of the list of cells at every dimension. So during my PhD thesis and work, I've been working in different problems in low-dimensional topology, and I've been interested in the study of the homotopy type of CW-complex of lower dimensions or low dimensions, and in particular, I was interested in to apply Morse theory. But the problem is that also I was interested in two things. First thing is to really construct, describe this complex, and also was interested in the description of the kind of homotopy equivalence that connects this original complex K with this new complex Km. So the main idea to connect the notion of, or the idea of collapsibility and the notion of, or the theory derived from discrete Morse theory, or all these transformations that you perform in your complex to obtain Km, is the notion of internal collapse. So this is sort of generalization of the notion of collapse, because you have a collapse, but perhaps you attach a new cell to the bigger complex. So suppose that you have a collapse, but then you attach a new cell here. This cell might obstruct the collapse that you have from K to L, but you still want to perform this collapse. So first of all, what you need to do is to define a new touching map of this cell, and to attach this cell with a modified touching map into L. So one thing you can do is to compute the composition of the original touching map with the retraction induced by the collapse. And then what's the connection between these two complexes? Well, there is a very specific way to connect these two complexes by means of an intermediate complex here. So suppose that all your complexes has dimension, I mean, K, and also the cell En has dimension, each of them has dimension less or equal than N. So then you can construct here a complex, let's say a cell of dimension up to N plus 1 that collapses to both complexes. Great, so this is related to discrete Morse theory, because suppose that in a very simple case, you have a collapse from K to L that are two different sublevel complexes, and this collapse is related to the different non-critical cells. But then you have a critical cell at some point that you attach to K that obstructs this collapse, but you can still connect these two complexes, the first complex and this modified complex. And this is the idea, the building step of the construction of the Morse complex, the CW complex. Then suppose that you want to iterate, so you have a new, let's say, critical cell here, E and prime. And then the idea is to try to reconstruct or construct a new attaching map on top of this new complex. But then if you keep track of this intermediate complex, you have here an inclusion, and also here you have a retraction, and then you can compose the original attaching map here of E prime with all these two maps, and then you have a new attaching map, let's say here, E prime and tilde. And then you can also construct again, so here, an intermediate complex, let's say Z prime, that collapses to both complexes. So you can iterate this process. So this is, so it looks horrible, but the idea is that you can iterate this process. You have K and you attach different cells, all of dimension up to N. And then you have the different attaching maps of each of these cells. And then the main, the main idea is that you have a collapse that it's internal in the sense that you attach new cells here on top of K, but you still want to perform this collapse internally. So you need to construct, so you need to modify the attaching map of all these cells that you have attached on top of K. And you can really perform this iterative procedure that I described before. So you have the first modification of the original attaching map of the cell, the first cell that you attach, and then you compose with the inclusion and retraction of related to this intermediate complex that you have here in the middle. So, and this complex, something that is important is that this complex has a dimension up to n+1. This is going to be really important in a minute. Great. So with all these all these ideas in mind, this is a sort of new statement of the main theorem related to discrete Morse theory. So you can have a complex, let's say of dimension n, and you have a discrete Morse function. Great. So then this, you have this sequence of sublevel complexes, okay? And you have two different situations. Either you have critical cells, so you have collapses, or you have a collapse, or you have critical cells here. So you attach to the previous sublevel complex new cells that are the critical cells. Okay, so this is the case of the critical cells, and this is the case of the non-critical cells. Great, so all these collapses can be performed internally. So you have to modify the attaching map of all the critical, the original attaching map of all the critical cells in the way that I showed you before. So again, here you have to iterate again the procedure that I showed you in the previous slides. And you have a sort of description of the Morse complex. I mean, it's complicated, but it can be, at least in lower dimensions, it can be completely described with an algorithm. We're going to see this in a minute. So you have a description of, at least some sort of description of the Morse CW-complex, and also you have a description of the kind of homotopy equivalence that connect the original complex and this new simplified complex. And these two new pieces of information are going to be very important in our applications. Great, so just to show you here how it works in our example. So here we have the original complex. The cells in orange are the critical cells, and then you have with arrows the internal collapses. So here you have an internal collapse. I mean, this is a collapse if you remove this cell. So let's keep track of the attaching map of these cells. So suppose that this is oriented in this way. So we can describe the attaching map as with letters like X2. This X2 represents these cells. So suppose that one cell is oriented in this way, X2, X13, and X3. And we're going to, if you orient these are in this way, so this is to -1. So this is a touching map of these two cells. Then you perform this internal collapse. What does it mean? So like in the regular collapse, you remove this pair of cells, these two cells and this one cell. So you remove this pair of cells. So and then you modify the touching map of all the rest of the two cells. So in this case, you have here this one cell that does not exist anymore in this complex. So you modify the touching map in this way. So it's very simple to describe the new touching map algorithmically. So let me write. So the new touching map is going to be x2 to the -1, x12, x4. Let's say it's oriented this way. So you have, sorry, it's oriented in this way. So if this is the orientation of the two cells, x4 to the -1, x3. So you replace, so what's the internal collapse? You remove this pair of cells and then you modify the touching map of the rest of the two cells. So you replace this, one cell with this list of these two cells. So you can iterate this procedure and then you have a description of, so if you start with K, here you have a description of the Morse complex. This is very nice decomposition of the torus. Great. So let's try to use these ideas in the computation, in the study of group presentations. So as you know, you might have a group presentation. It's very difficult to understand the group behind this group presentation. It's not tractable computationally, but sometimes we are looking for efficient presentations of groups. So let's try to use more theory to do that. There is a nice correspondence between CW-complexes of dimension 2 and group presentations. So this is going to be the bridge. So this is very well known. So every time you have a presentation, you can construct a CW-complex, of dimension 2 that is called, in this case, the standard complex, KP. So you have a single vertex always, and then you have one cell of dimension 1 for every for every generator. And also you have a cell of dimension 2 for every relator. And the touching map is related to the relator, the word that describes the relator. Of course, you have to choose some orientation in the one cells. And the property of this complex is that its fundamental group is the group represented by P. Conversely, if you have a complex, then you can construct a presentation that is going to be a presentation of its fundamental group using the following procedure. So first of all, you need to identify a spanning tree in the one skeleton, and then you collapse this spanning tree in one point. So you compute this quotient, and then you compute a fundamental group of this quotient. That is basically this presentation. So you have one generator for every cell of dimension 1 that is not in the tree. And also you have one relator for every two cell. In general, these presentations are huge because you have as many relators as cells of dimension 2, and also as many generators as cells of dimension 1 that are not in the tree. So you only save like n-1 cells that are the cells in the tree if you have a complex with n vertices. So something else to say related to this presentation is that it is a presentation of the fundamental group of K, but it not only encodes information about pi1 of K, but also about its homotopy type. We're going to see this in a minute. So this presentation is very powerful to understand K. Great. So as I said before, this is a presentation of cell times cell, a huge presentation of this group. But suppose that we want to simplify this presentation. So we first associate some Morse function or define some Morse function on top of K. And then we are able now to really understand the Morse complex. So we compute here. So let's go down. And here you compute the Morse complex. And then you compute the standard presentation associated to the Morse complex. And in our case, this is a very small presentation of the same group. So this is some way to obtain equivalent presentations of the same group, or more simple and smaller presentations. So all this stuff, at least in dimension 2, can be performed algorithmically. So I have an algorithm that tells you, if you give me a regular complex of dimension 2 and a Morse function with a single cell of a critical cell of dimension 0, there are I have algorithms, I coded algorithms in both Sage and also GAP to compute the Morse presentation, that is the standard presentation of the Morse complex. So you simplify K and then you compute this presentation. So let me show you. So these repositories are, are open, public. So in the repositories you have this. Oh, let me show you. I have problems with Zoom here. Let me show you here. So here, this is example of the CW complex in the slides, and then you have description of the original attaching maps. And here I describe the Morse function, or which is equivalent the cyclic matching in the phase posets associated to this complex. And then if you compute the Morse presentation, you have this presentation that is a very small presentation of cell times cell. So this is a presentation associated to the Morse complex. Okay, great. So well, so also this coding gap, and well, there is a similar, or there's a related algorithm also in this paper. Great. And this is the pseudocode of this algorithm. I mean, I don't want to look at the details, but the idea is that you start with the touching map of all the two cells, and then you modify the touching map also every time you have this internal collapse. So this pair of cells, you remove this pair of cells, like in a regular collapse, and then you rewrite the touching map of the rest of the two cells. So this is the idea of the algorithm, basically, like I show you in the example. So now I would like to apply these ideas in these two problems. First problem is the Andrews-Curtis conjecture. So this conjecture is a conjecture in combinatorial group theory, and this is the statement. So it is a conjecture that is still open from the 60s, and it says that suppose that you have a balanced presentation of the trivial group. That is that you have same number of generators and relators, and the group associated to P is a trivial group. Then you can always transform this presentation into the empty presentation. This is a trivial presentation of the trivial group by a finite sequence of the following operations. So these operations are operations mostly in the set of the relators. So you can replace a relator by its inverse, by the multiplication with another one, or by conjugate. Also, so notice that operations 1 up to 3 don't change the size of the presentation. But operation number 4 allows you to add a new generator and also a new relator that is the same as the generator. So at this point, you increase the presentation. Also, you can apply the inverse of this operation. So if you identify a generator and a relator that are the same, then you can eliminate both. Great. So this statement might remind you this theorem. due by Titze. So this result says that, so it's very similar, but with a crucial difference. So if you have a finite presentation of any group, in this case, any number of generators and relators, then this presentation can always be transformed into any other presentation of the same group. For instance, if you have a presentation of the trivia group, you can transform it into the empty presentation by a finite sequence of the following operations. And you can see that these operations are basically same operations as the operation proposed by Andrews and Curtis, and also the operation number 5 that allows you to add a new relator equal to 1 or delete a relator equal to 1. So notice that operation number 5 changes the efficiency of the group. Also, if you think about these operations in terms of the modification that you perform, so here to every presentation you can associate the standard complex, okay, the complex associated to the presentation. So each of these operations is some modification of this complex. So operation 1 up to 3 just modify the attaching map of the two cells associated to this relator. Operation number 4 adds a new generator. That means that you add a new cell of dimension 1, and you also add a new cell of dimension 2 that is attached like in a disk, okay? So operations, you can see that operations 1 up to 4 don't change the homotopy type of this complex. But operation number 5 is basically the attachment of a sphere on top of the vertex of this complex. So it changed the homotopy type of KP. This is the main difference between operation 1 up to 4 and 5. Great. So what about this conjecture? So there is a list of potential counterexamples. That is a list of presentations that are balance presentations of the trivial group, but there is no sequence of, it's not known sequence of Andrews-Curtis transformations to transform these presentations into the empty presentation. Some approach related to these counterexamples and also to the conjecture in general is are associated to the search for all, some subset of all the possibilities, all the transformations that you can perform, starting with some presentation at the beginning. In general, these algorithms only use operations 1 up to 3 because or operation number 4, but only the inverse, the reduction of the presentation. They don't try to increase the size of the presentation. And also, I want to say related to these kind of algorithms that there's a theorem due by Britson in 2015 that says that there exist balance presentations of the trivia group that satisfy the conjecture, but the minimum length of any simplification sequence is huge. So you might have, if you use this kind of algorithms, you might have bad luck, so your algorithm is not going to finish, even though it's a presentation that satisfies the conjecture. So let's try to use topology to deal with these examples and also with this conjecture. So the first connection with, the main connection with topology really is in the original paper, and it's an observation of the anonymous referee. So this is very curious and special. So the anonymous referee of this paper noticed that the operations proposed by Andrews and Curtis are in correspondence with free deformations of two complexes. So, so what does it mean? So it means that if you have two presentations, P and Q, And then you compute the associated complexes Kp and Kq. Then it's the same to have here an Andrews-Curtis transformation bridge between these two presentations, than to have a free deformation between these two complexes, which means that you can find your an intermediate complex of dimension d that collapses to both subcomplexes Kp and Kq. And also in the other direction, you also have a connection. And also the referee mentions that this conjecture, the Andrews-Curtis conjecture, can be completely understood in terms of simple homotopy theory by means of this connection. So suppose that you have a complex that is contractible. So this is the analog of the balanced presentation of the trivial group. And it's well known that you can always find a simple homotopy equivalence between the original complex and a point. So that means that you have a sequence of expansions and collapses. And it's also true that if your complex K has dimension n, then you always have an n+1 deformation. If the dimension of the complex, that is n, is different than 2. For the case n equal to 2, this statement is open. And this is the analog of the conjecture of the Andrews-Curtis conjecture from a topological side.
And Ximena, n+1 there is the dimension of the complex that's needed.
Yes, so here this means that if the dimension of K is n, then you can always find a complex of dimension n+1 that collapses both to the point and to K.
Thanks.
Great. So here is the main idea using Morse theory to study the conjecture. So I will explain. This is a corollary of the refinement of the main statement in discrete Morse theory. So suppose that you start with the presentation, and then you construct the associated complex. Okay, great. So now this complex, I cannot apply Morse theory in this complex because it's not regular, but you can subdivide it. You compute the barycentric subdivision, and it is now regular. Then compute some Morse function on top of this complex. And then once you have a Morse function, we have some tool that tells you, well, so you can simplify it and compute the Morse CW-complex. Great. And then you go again to the level of presentations, and you compute the presentation associated to this simplified complex, Kp prime M. So now we prove that between the original complex and the Morse CW-complex, we have an n+1 deformation. In this case, it's a free deformation. So then, because of the observation of the referee, we have an Andrews-Curtis transformation between these two presentations. And this is the idea. So you start with the presentation, you use Morse theory to construct this new presentation, and this refinement of the description of the homotopy equivalence allows you to say that these two presentations can be connected with a sequence of Andrews-Curtis moves, even though we don't know the list of moves, and we have seen, because of the theorem of Britson, that is not, perhaps this is just too bad to look for the explicit sequence. Okay, so this is the main idea, to deal with presentations with counterexamples. So of course, this is a subset of the full list of potential counterexamples, but with this strategy, I proved that these potential counterexamples do satisfy the conjecture. So what's the main idea? Well, the main idea is you start with the presentation, and then you construct, so you follow this pipeline here, and you have a new presentation here. And in most of these cases, it's very easy to construct a Morse function, and a new presentation that is very easy to study and to trivialize. So you can go to this notebook that is in the repository, look at the presentations and perform this. I mean, here I compute more function in terms of acyclic matchings in the phase poses. So it's a poset associated to the presentation. And you can really see that, I mean, this is an algorithm that takes some seconds, I mean, less than seconds, and you can prove that these potential counterexamples satisfy the conjecture. So I will move to the new, the second application, but of course, if you want to ask some question related to this, we can see this by the end of talk, or I mean, whenever you want. So I want to move to this new application. So this is a very, I mean, it's a work in progress that we started with Kevin.
Excuse me, Ximena,
yeah.
Can I ask a short question? So
Yes.
this method of yours, does it allow in principle to recover the sequence of AC moves which trivialize?
No, and I mean, this is, so perhaps you can recover, have an estimation of the number of moves that you might, I mean, you probably have done, but I don't, so so you have this bridge because, so if you want to reconstruct these moves, then you have to reconstruct the free deformation between, there is the complex and the Morse complex, and then use this correspondence proved by, I mean, or noticed by the referee. So every time you have free deformation, you can identify some Andrews-Curtis move or set of Andrews-Curtis moves. So it was not my idea to compute this sequence of moves.
But this is possible to do if one is interested, right?
Yes,
So,
but you need to reconstruct the sequence of free deformation between these two complexes, and then compute the analog of each of these free deformations in terms of Andrews-Curtis transformations. So it is possible. I haven't done it, but it is. So at some point you have a sequence, but I don't compute it in my algorithm.
oh, thank you.
So the warranty that there exists some sequence is given by the free deformation, and that's all. Great, thank you for the question. So I was saying that this is a work in progress. It's in a very early stage, but I want to tell you at least the starting point. So the motivation of this application is, again, I mean, the inference of topological properties of a sample from topological space from a sample. And with the idea, we're looking for algorithms to achieve that, like in the case of persistent homology. Now, the motivation to focus in pi1 or to look for some other invariants different from homology is that, of course, homology, persistent homology inherits all the problems that has homology. That is that, of course, there exist examples of topological spaces with the same homology but different homotopy type, okay? So, yeah, so the idea to try to find some, extract some information about pi1 is, again, the notion of the idea of persistence. So in general, you start with the point cloud, you construct in some way the filtration of complexes, and then you apply your favorite topological invariant to both morphisms and complexes. And you study the evolution of all these objects. In our case, we're going to apply pi1. The problem here is what's the algorithm to compute all these objects? So I've shown you some algorithm to compute the presentation of pi1 using trees, but in general, these trees, I mean, these presentations are too big. So the starting point is to suppose that we want to use Morse theory. So we define a Morse function on top of the last complex of the filtration, okay? So once you have defined this Morse function, you can restrict the function to each of the complexes in the subcomplexes in your filtration, and you still have a Morse function. So you can compute the reduced complex at every level of your filtration. Great. You lose the property of this being a filtration, but it doesn't matter because we're interested in the fundamental group. So we have an algorithm to compute a presentation of pi1 of the Morse complex at every level of the filtration. The problem is that this is too inefficient to run this algorithm for every level of the filtration. And also we are interested in the morphisms. So how to do that? Well, so the good news is that I realized that, so suppose that you have your filtration and you focus on the last complex of your filtration. We're going to assume that all lower complexes are connected. So you compute a Morse function on top of the last complex of your filtration. And then you run the algorithm that I showed you that exists before. And then you compute a presentation that is in a way efficient or small, depending on the Morse function, of course, a presentation associated to the simplified complex, the Morse complex associated to the last complex in your filtration. So this procedure has a complexity m squared with m, the number of choices in the last complex. Then what I realized is that a slight modification of this original algorithm with the same complexity allows you to compute the presentation of all the previous of the fundamental group of all the previous Morse complexes in your filtration, and also allows you to compute morphism between these group presentations, all these morphisms. So with the same complexity, you can compute everything. So complexity depends on the size of the biggest complex. So I think that I have, I mean, this is a pseudocode. I want to show you, I mean, it's a bit, I mean, complicated to explain the details, but the idea is that if you compare the original algorithm to compute the standard complex, sorry, the standard presentation associated to a complex, using more theories, so this reduced presentation, or you want to compute given a filtered CW-complex, the presentation associated to every stage of the filtration, you have to add a couple of lines that keeps track of the level of the filtration which you are. Great, so let's, I will end with that example. This is a very small example, so you can run this example by hand to check. So this is a very small sample of wedge of spheres, and this is a sample of a square with a boundary identified like in a torus. And these are the persistent barcodes. In the example, we're going to use the victorious group filtration. And something that I didn't mention before, or I mentioned very briefly, is that I'm going to assume that all my complexes in my filtration are connected to avoid the technicalities related to the base point. So for these values of the victorious group filtration, I am not going to perform any kind of analysis of pi1. Right. So this is, I mean, this is a very simple example, a very small example, and this is some complex of the victorious filtration. And this is a computation of the persistent fundamental group with the idea of discrete Morse theory. So for these values of the filtration, so this is this is victorious groups alpha. And then, I don't know if you can see, but there are some arrows that represent the Morse function or the cyclic matching that I have used to compute the simplification of the Morse complex associated to this Vietoris-Rips complex. And then here I compute the presentation associated to the Vietoris-Rips alpha for these values of alpha, simplify using this cyclic matching. And also this is what happened for these values of alpha, and also same for these values of alpha for this complex, for these complexes. And in terms of the morphisms, well, so this morphism is trivial. So you have morphisms of presentation. So here every generator goes to 1, and here every generator goes to, so it's mapped to x16 in some cases, x17 in some cases, so 1. The morphisms are related to the internal collapses. So you can reconstruct the morphisms, and these morphisms are related to the internal collapses. If you compare with the persistent barcode, so you have here 2 generators in this interval that are associated to, so this free presentation, this free group. And here you have this presentation that is associated to this interval if you compare with homology, and also this free group that is associated to this interval here. So, we have some way to compute all these morphisms and all these, let me show you. So all these morphisms and all these presentations, you have these commutative diagrams, but of course there is a lot of work to be done. So I will end with this slide. So this is a lot of information. It's very difficult to work with group presentations. As you can see, there are many conjectures related to group presentations. So the idea is to extract some group invariants that persist over different values of the filtration, and also to find some sort of graphical representation of some properties of these groups and also morphisms that complement the information that you have using persistent homology. And we're working in code, in GAP and SAGE, to look for more bigger examples. And what happens, of course, the efficiency of the presentation depends on the choice of the Morse function. So we're looking for some sort of canonical way to choose more functions or acyclic matchings in the phase poset if you are working with Vietoris-Rips filtration, because you have a lot of structure in these complexes. Also, we would love to have some stability result. And of course, if all this theoretical part is done, we're also looking for applications in real data. Thank you for your attention, and I'm open to questions.
Thanks so much. So before we get to questions, let's briefly unmute ourselves and applaud for Ximena. Questions for the speaker?
May I ask a question? Do you know how this Morse theory that you are using, is it in any way related to the one version that Bistvina and Brady developed?
Oh, I didn't develop a new version of Morse theory, just compute some explicit description of the different pieces of information that you can extract using the original or the Foreman discrete Morse theory. So this is not a new version. I know that there is a nice and recent paper due by Zaremski that connects Bistvina Brady's Morse theory with Foreman's Morse theory. But what I've done here is not a new version of Morse theory, but sort of more explicit description of all the information that you can extract using the original version of Morse theory. So in this paper of Zaremski, you can find, I mean, yes, so there is a connection between these two theories, but here I'm just using the original formal theory.
Thank you. Henry sent link to the Remsky paper in chat. Yeah, thank you for this information.
And yes, something else. Yes, so, and also related to Ximena-Brady theory, I would love to use also Ximena-Brady Moore theory to achieve. I mean, it's more general and more perhaps more powerful in some cases. So yes, so I'm also looking for some new ideas that can related to Ximena-Brady theory, Moore theory to use in these problems.
That's a great question. I think there's problems that our community could solve better if we had more familiarity with the Ximena-Brady Morse theory.
Yeah. Yeah. So I'm still looking for, for how to use the Ximena-Brady theory, because we have a trade-off between it's more general, but I mean, you need to in the end be able to compute things.
So I had a question, Ximena. I understand that the translation between the sort of Morse collapses and the AC operations on groups gets complicated, but you did sort of establish this nice correspondence between some of the operations you would perform on a cell complex or on a group, such as, you know, adding a single 2-cell, which changes the homotopy type, or adding a single edge and a disk. So when I think of a Morse collapse, right? So maybe I contract an edge into a triangle, leaving only 2 edges. I can still think about that in group theoretic terms, where I'm taking this generator and removing the generator while I remove the relation, explaining why this generator is redundant. Is that right?
Yes, I think that also I have, so in this example, so let me show you, I have some slides in the end that are related to that. So the idea is that all these internal collapses can be, in the case of dimension 2, can be translated one-to-one into some modifications in the presentation. So if you start with the presentation of the original complex, and then every time you perform an internal collapse, so here, I mean, this is a presentation of the presentation that you obtain when you use trees. So every time you have a Morse function with a single critical cell of dimension 0, you can identify a spanning tree in the one skeleton. So this is the spanning tree that you can use to compute, I mean, in the original case, the presentation of pi 1, or the standard presentation associated to the complex. But then every time you have, so every 2-cell in this presentation, like this 2-cell is this relator here. And every time you perform an internal collapse, what you have is here, I mean, this is the generator associated to this 1 cell. And if you eliminate, so if you eliminate, sorry, I made a mistake. So this is the generator associated to this 1 cell, and this is the relator. I think that I'm right. So you have x13, x12, x4 to the -1. So this is the I mean, I am right, or x13. Yes, I think that I am right. So give me a minute. Yes, so this is correct. So this is the relator associated to these 2 cells. Okay, so then every time you perform an internal collapse, what you do is to eliminate these 2, this generator and this relator. And then every time you have x13 here, what you do is to you replace x13 in the rest of the relators by x12, x4 to the -1. So every time you perform an internal collapse, what you do is both these operations in this group presentation. So you remove a pair of both generator and relator that are the associated to the one cell and two cell that you remove, and also you perform the modification of the rest of the relators in terms of this relator that you have already removed. So because you don't have this generator anymore, so every time this generator appears in the rest of the relator, you have to replace it. And this is basically the algorithm that computes the presentation associated to the Morse complex. So basically you stay with the presentation and you start to compute these modifications. Every internal collapse corresponds to this set of operations. So this is a great question. This is the core of the algorithm.
More questions? I have one more question. So, you know, your algorithm was quadratic in the number of two cells. So I don't know if this is way too optimistic, but, you know, the standard persistence algorithm is cubic, you know, in the number of simplicities. I mean, is there any hope for, you know, faster algorithms, or is that just, am I misleading myself?
Yes. So, I mean, it's quadratical, which means it's better, but it's still big because, I mean, there are two, so disadvantage, one of the disadvantage here is that you have presentations, so you have more information, but you have to deal with this more complex object. Also, when you have, it's in the original case, so these are complexes of, well, so here. So here you have this filtration, and in general, the filtration has many cells of every dimension. Mm-hmm. So you're only interested in the critical cells. So this is perhaps, so M squared, I mean, M here is, so it's quadratical in the number of two cells that you have. Sorry, the critical two cells that you have.
Critical two cells, I see.
Critical two cells, yes. So if you have a very bad Morse function with many critical cells, then so here this M is going to be like, I mean, the upper bound is the number of critical of the two cells of this complex. So in general, I see. So the complexity depends on the number of critical two cells.
Gotcha. So you can't make that direct comparison.
Yes. So yes. So this is why we are looking for good Morse function, canonical Morse function that you can build on top of complexes, so some standard Morse function. So now what we are doing is just to generate some Morse function that is with a greedy algorithm. But it's very important to have here a good Morse function.
All right, maybe let's end with one last question in the chat. In terms of applications, could we use this technique with relation to surgery theory by a sequence of spherical modifications? For example, looking at the collapse of a two-sphere with a hole.
Looking at, sorry, I didn't catch the last. Looking at the collapse of a two-sphere with a hole. Yes, so I think, yes, so there's something that is very interesting to, I mean, at least for me, that is that, so here you have, so every time you perform this, simplification of your original complex, you perform all these sequence of internal collapses that are, I mean, they mean n+1 deformation. So if you look at these ideas only, I mean, theoretically, so yeah, so probably you could use the technique. I mean, I'm only here using complex of dimension 2, but perhaps for higher dimensions and surgery and all these kind of theories might be used. But I haven't thought about, for instance, higher dimensions in which perhaps surgery is involved to really capture or reconstruct the touching map of the higher dimensional cells. but yes, some way or some path to continue.
All right, so for today, our time is up, but thanks so much, Ximena, and thanks to all the audience members for joining and for the nice questions. So